Thank you very much. Good. But basically, thank you all of you that are organizing Mr. Pedro, but also Danuta, Rebecca, and Gianni that are keeping alive these webinars. This is a great idea, and I hope that we continue, into the time after this Corona crisis. Well, hope you recognize here is a temple molecule, but let's go to the more official presentation of the talk here. This is a work that I am going to present that was done in the group of Professor Stapf here in Ilmenau. And then most of the experimental results that I am going to show here are measured by Oliver Neudert and Gizatullin. Oliver Neudert came here as a postdoc and started the project basically. And after that was continued by Bulat, and he is going to defend his thesis just in a month, more or less. Well, Danuta already says a few words about the DNP. I will not say more than this, but basically DNP is taking advantage of the big polarization of the electrons. This is a classical plot that we see here, and then this classical equation. Then we see here that there is a way to transfer the polarization of the electrons to the nuclei through this DNP. This is realized by irradiating a radio frequency in the right frequency, basically in the sigma level of the electrons, and is used basically right for increased signal sensitivity. For example, we see here a classical plot where we have the thermal polarization on the left, and then you have the Boltzmann population here, and then basically the polarization is related with the difference in the population of the energy levels. That is, on the right side you see much more difference, and then you get not only signal intensity, but you get a huge, a very much better signal to noise ratio. And due to the interactions of the spin of the electrons, the free electrons and the nuclei, basically it happened this coupling and this phenomenon of DNP, and actually this interaction is modulated by the dynamics of the molecules that are contained in these electrons, like the radicals, for example. And then that's why DNP also could give us a lot of information about dynamics in the system. And I will talk also about how we can eliminate also a certain influence that this interaction has on the relaxation of the nuclei itself. But what is about in field cycling and DNP? First of all, for DNP, we need the presence of these electrons that are carried by the radicals, for example. And then there is a lot of work done in field cycling, basically with samples of interest, with the nuclei of interest, and radicals, not with DNP, but field cycling combined, studied system, molecules with radicals. And then, for example, the group that notates herself, and the group, for example, of Florence, Benatti here in Germany, Jean-Pierre Korb also show us something, and then many others that I forget, of course. But it's quite interesting to study this because these interactions give us a lot of information about the dynamic of the system itself. But again, we still didn't say anything about field cycling and DNP. This is a question that always, Gianni, we met Gianni several times in several conferences during last years, and he always asked me, or Fig as well, what is good DNP? The combination of DNP and field cycling. This question is difficult to answer, but okay, maybe after this talk we could get some light on answers on this question. And let's see, there is some precedent, some formal measurements related to field cycling and DNP. Actually, yes, this was done by David Lurie many years ago. And still today, they are doing little things related with this to calibrate the magnetic fields. But in that time, there are several papers. And I mean, David Lurie in Aberdeen and his colleagues there measured here basically a DNP effect using field cycling. That means they have a sample of tempo, a radical, we will see structured later in water, or to change the dynamical properties of this radical and the solvents. Here they add glycerol in the system. And then you can see here these curves. These curves are obtained, irradiating on the fixed microwave. Okay, at the fixed frequency here is around 300 megahertz. And then they change the polarization field. Then they get these experiments. I think they are motivated by imaging. I mean, to get better contrast, to better sensitivity in imaging. But in order to see which parameters they can control to get better enhancements, they had to perform such an experiment. Let's say changing the dynamics of the sample in order that they change the dynamic of the molecules, and then they see the effects on the enhancement here in arbitrary units in this plot. We see 3 lines here because the tempo has in EPR, let's say the EPR spectrum has 3 lines due to the interactions of the electron basically with the nitrogen 14 in the sample that has a spin 1. And this experiment basically is a pioneer experiment for us, and it seems like an inspiration for us. Yeah, I find it actually nice, and it's on the same spirit that we are doing our experiments here and extend applications. Well, then to outline the rest of the talk, okay, we will see some small principles of basics of the how we can describe the enhancement in DNP. After that, the experimental setup. After that, I will describe what we call the difference method, the so-called 5-and-dime introduced last year in our group. And then I will show some examples and give an outlook. Let's start then with the beginning. Then as we mentioned before, DNP happens when we have interactions or coupling in between the electron spins and the nuclear spin of the species of interest. In this case here, we have electron and proton with both with spin 1/2. And we see the classical here energy level with these spheres are representing not real, but schematically the occupancy of these levels here. And then we see the big separation corresponds to the electron levels, and then the small separations crossing is the nuclear levels. And then these are couple spins, 2 couple spins. Well, then if we irradiate the system with microwave in the microwave region, then what will happen is that will be a saturation of the energy level of the electron, because we are irradiating at this frequency. And we happen also here cross relaxations, and then we describe this by these functions omega 0, 2, and 1 that will describe the nuclear relaxation, but the cross relaxation are done by these double quantum and 0 quantum transitions here. And then the detail here is that this omega 0 and omega 2, when one is bigger than the other, 2 different effects we happen here called dipolar and dipolar interaction or scalar interaction. We'll see this later. But okay, we have this, and then during this irradiation, the system evolved and then reached some steady state where in between there are transitions in between levels, and the W1 is the transition of the nuclear system induced by this mediated by this electron nuclear interaction. The W10 is just the nuclear interaction basically that produce differences. Evolution in the levels, in the population of the levels of the nuclear level, and that at the end will cause relaxation. And Well, let's see. Then, what I described until now is the Oberhauser effect, right? There is also another effect that is the solid effect. That this happens when we have mixtures in between levels, and this mixture can be described by a linear combination of the states there, and then the XQ is the mixing factor, and P plus Q is 1. I mean, the sum is 1, and then the Q is the factor that will describe, basically, will be responsible for this solid effect, where if you irradiate the transitions of the electron system, then you will have transitions that are allowed in principle. Then when you have the mixing, forbidden transitions will also happen, then you will have this solid effect. The details of the solid effect will happen at the shifted frequency or in an offset where is basically the Larmor nuclear frequency, nuclear Larmor frequency. We'll see also this again. Well, then this is the Q factor, and then, sorry, the Q mixing factor, and then the enhancement is described by this classical equation that we see here on the screen, and it's described by 3 parameters, basically. That means when you irradiate, you reach a steady state, and then when you arrange the terms, you can see the enhancements as the comparison, let's say, the ratio of the the signal after irradiation and the thermal polarization that we got when you don't irradiate. And then you have the 3 factors: your coupling factor, leakage factor, saturation factor multiplied by the ratio of the gamma. And then this is basically the key factor. If all the factor will be 1, then you have a theoretical enhancement there proportional to the ratio of the gamma, or the electromagnetic ratio of the electron with the respective nuclei. Well, then let's try to describe this fast. The leakage factor is basically describing how how effective is the let's say the electron-induced relaxation with respect to the complete relaxation. That means if the relaxation induced by the electrons will be dominating, then this factor will be 1. We can see this in the equation on the right, in the second equal here. Sorry, I will start to use the pointer here. And we see that this is a combination of the transitions here, ratios. And then this factor depends on the radical concentration and also on the accessibility of the nucleus to the electron, basically. I mean, because the closer you are, the interaction there is more important. And then this I will come back to this spherical hindrance when I will show a bit the structure of certain radicals. And then again, and I will slow down here a bit, you have to take into account that we are trying here to describe dynamics at the end by all these experiments, dynamics that will modulate the interactions in between the spins of the electron and the nuclear species that is of our interest, basically. Let's continue here with the other factor. I mean, the next factor that we have to describe is the saturation factor here. And then we can describe this by the formula here, but this equation on the right side. And you see that this saturation factor depends on the magnitude of the microwave magnetic field in this omega-1, basically. And then on relaxation properties here. That means also depend on the type of radical. And we can see this easily here in the factor 3, where the factor 3 is the number of lines in a particular radical that I choose here to describe this formula and this tempo that have 3 lines in the APR spectra here. Also, this saturation factor will depend on the radical concentration and this is described by the process of an exchange process, and this is called the Heisenberg spin exchange process. That we can go in detail maybe for questions, but not now. But we will see the effect of this Heisenberg exchange in the S factor here, in the saturation factor. And then, what happens if we increase concentration, for example, of the radical in our solution, our liquid, in water, for example? it happened that the line width of this spectral of the lines in this spectrum will increase. Let's see an example here. You see temple in methanol, for example. We have the signal, the EPR signal, recorded at different concentration. You see here at low concentration, you have very well-defined three lines, but when you increase the concentration, then you have only one line. And this will have a direct influence in the S factor, and we can describe this by the Heisenberg exchange factor. Well, also we have some affecting the homogeneity of the field through this term here, omega 0, basically. And now we can describe how experimentally you can access this factor, basically. I said before that the omega 1 is proportional to the B1, basically here, and then this is proportional to the power. This will depend on our resonator. BB squared depends linearly on the power. Then if we put this in the equation, we can write actually the encasement factor in the way that is here highlighted in blue. And you can then try to measure the encasements at different powers with certain concentration, fixing this coupling factor and the leakage factor here, the two other factors. And then you can represent this as inverse, as a reciprocal of the 1 minus E, and then in function of 1 divided power. Then you get straight lines. And then you see, if you increase the power, you go to the 0. If you go to the infinite power, to the high power, then you will get the maximum encasement. You can see this in the equation blue here. And this is used basically to find out the maximum encasement, these extrapolations, and like this, you are able to find the coupling factor. Because at the end, the leakage factor, which is here, sorry, that is highlighted here in the circle, the leakage factor is, we can consider that if you have very, very good efficiency in the radical induced relaxation, then it's 1. And then you can find here the coupling factor with this, doing this measurement. And what is the effect on of the Heisenberg exchange? Okay, it can be taken into account here in this expression by this omega exchange here. That is basically the exchange rate of the spins of the electron spins, basically, in this exchange process called Heisenberg exchange. This can be measured. How? Okay, you measure different concentrations, and then you measure the line width of the lines in the EPR spectra, and then this is proportional to the slope of this curve. Then you get this equation. Then, with the help of EPR, then you can measure at the end here this coupling factor. And why is important this coupling factor? Let's go to the description of this coupling factor. Sorry, I put this slide here. Even I am not an expert in EPR basically, but here we see that the saturation factor, you have also relaxation property of the electron, and this can be measured basically with EPR, yeah, like T1 or T2 of the electron spin. And here I show here just an Neudert experiment where in this tempo the nitrogen 14 is replaced by nitrogen 15 that has a spin 1/2, and then you see here that you have two lines in the spectra. Well, the coupling factor. The coupling factor depends also on the type of radical, type of molecule also, and then depends on the temperature through the dynamic of the system, basically, and then of the magnetic field. The coupling factor is described by this, by the difference in the ratio omega 2, W2 and W0. And as I mentioned before, depending on this difference, you have dipolar coupling or scalar coupling, basically. Well, why is important this factor? Because this factor, when you go to into the description of this factor, you see here that on the, I mean, this part is related here with the paramagnetic induced relaxation, basically, with the electro-induced relaxation in the system. And then here is the difference of these two transition probabilities. And then the transition probability at the end are described as spectral density functions. And the spectral density function is what has the physical meaning, basically, or let's say, are the Fourier transform of the correlation function that is what basically has the physical meaning. And then that means we have dynamics in this spectral density function. That means knowing this coupling factor, we can get information about the dynamics. How, okay, modeling the coupling factor with a certain spectral density functions and check if this is, I mean, if we get a good agreement of what we measure and with the model that we implement. And a lot of work is done today in order to describe the dynamic of these radical nuclear radical solutions systems in order to get the right spectral density function, in order to model the dynamic, basically. And then you see the coupling factor here is a combination of rotational dynamics and diffusional dynamics, and also on the scalar interaction here. And then if we, this is a typical curve here, and then sorry for this ABCD here, I know what happened, but basically the red line here is the scalar contribution here. Then you see that maximum, I mean, goes to -1 here, and then it's not dependent of the magnetic field. And then you see here the black line. You can see here the black line is the one that is related with the rotational correlation about the rotational dynamics. And the blue line here is related with the diffusional dynamics. You see that it is broadening a bit the theoretical Lorentzian line type. And then in the green is the total contribution. Then what we see here at the end is that, coming back to this equation, the enhancement that you can get here are at the end, the maximum values are being regulated by the ratio of the gammas, the ferromagnetic ratios of the electron and the nuclear that we have interest, and the coupling factor at the end. Maximum value 1 when you will have scalar interaction, 0.5 when you will have like pure polar interactions. Can be a combination of both. Well, talking about spectral densities, and here we see a bit more formal the equations for the relaxation transitions here, omega 0, 1, and 2. And then we see here also that the omega 1, 0 that is related with the transition of the energy levels of the nuclear, pure, yeah, without the influence of the electrons, and this is related with the T1 relaxation, basically, and then the W is related with the relaxation of the electron system purely, right? And then the induced transition due to the microwave are described by these three factors here, frequencies, 0, 1, and 2, and delta basically is the offset related with the EPR line, and then, or the electron transmission, sorry, and then you see that 0 and 2, you know, I do like this, thinking that you are I mean, I should do it like this here. Okay. The 0, 1, and 2 here contain the 0 and 2 contain this mixing factor, the factor Q, right? And then this factor Q is the one that is related with the solid effect. Basically, if you have solid effect, these transitions will be allowed, and then we will have certain effect. At which frequency? At the frequency given here by this line with here, where you have the central line defined by the electron transition, and then Fn will be the Larmor frequency of the nucleus. That means you will have here two lines, one in the central transition minus the nuclear Larmor frequency and plus the nuclear Larmor frequency. And centered here, you will have the V1 That means this is done by the, I mean, this speaks about the Overhauser effect exactly in the frequency of the transition of the electrons. Well, here I just describe a bit which type of spectral density function we have. I mean, all the spectral density functions will be described roughly by the Lorentzian function that we see here in the first square here. And the diffusional part will be described like this. And what I mean with rotational diffusion, we can see in this plot here that we have our radical, this green massive molecule, and then our little electron here. Nothing is in proportion here, of course. Then we have our nuclear here, right? And then the nuclear approach the radical molecule, and then will interact with the electron. And then transitions will happen, I mean, interaction will happen. But all these are modulated by the dynamic in the system. The dynamic in the system can be described here by rotation of the molecules itself, by approaching relatively to each other the molecules. And this is described by this diffusional spectral density functions, and the rotation described by the Lorentzian one. And then the correlation times here are basically combinations of the dipolar interaction, basically here, that is modulated by rotation and translational diffusion. We can see here that is a combination of these times here, yeah, right? And then this is I mean, these are defined here. I will say a bit about these times. And then the scalar interaction is related with the probability that the nuclear is close to the electron in the radical. And then this will depend on the time that this nuclear remains there and then goes later away. And then this is what we call nucleus lifetime here. And then basically the correlational diffusion time is related with the relative movement of both species here. And that's why is like this described here, like the sum of the diffusion of the nuclear and of the nuclear of the radical containing of the molecule containing the electron. Well, here's a bit more formal and much easier to recognize. The coupling factor here is basically a term that is related with the bipolar interaction they are very close to the nucleus in the solvation shell, to the electron, and then it's described by the rotational correlation functions here, rotational spectral densities, and one related with the correlation time, and then the omega related with the proton or the electron, right? And then you have another term that is the scalar interaction in the solvation shell, and then the dipolar interaction due to the diffusion, to the relative diffusion of the two species here. Then we can see here the expressions for the I will not go into detail on the spectral densities of the transition of the translational interaction here. Well, then if we manage to get I mean, this is a typical experiment done in field cycling. I will describe later a bit the experiment, but most of us here in the community know what we get here. And then these are the experimental, these are values that subtracted with the sample without radicals, we can get here the induced relaxation due to the electrons, I mean the nuclear relaxation due to the electrons. And then we see here that we can combine basically the different spectral densities here, and then you see here the contribution of all these curves that at the end will give the fit of the values that we obtain experimentally. This is just a typical example here, and then in this case of tempo in in difluorobenzene, we obtain these values here. And then you see that the TS is in between the pure the dynamics due to the rotational and the translational dynamics. Actually, not in between. This is much higher. We can discuss this. Well, and then this is at the end the coupling factor that we get after modeling when we obtain a good fitting of our experimental results with the respective and corresponding and correct spectral densities, then we can calculate the coupling factor, and then we got this kind of curves. And we see here evidently that it depends on the magnetic field. And in the X band are marked the values here, right? I don't know what I'm clicking here. Well, let's go now to describe the experimental setup and the parameters here. Good. We have in our community, I guess everybody will recognize the stellar spectrometer. We have also an EPR spectrometer here, benchtop, and then we have our probes for DNP that are double resonators here, and then we have the electronic for the DNP basically. And the samples, I will not describe samples, I will go through the samples when I give the examples, but here we can see a few examples of radicals. And I said that the radicals are massive molecules in general, and then you see where are the electrons here, and then now you understand the spherical hindrance that I was talking before, because the nuclear, to relax, imagine you have the water molecule is very, very small there, but has to come close to the part where is the electron there. And then this modulate also, this modulate directly the interaction in a dynamical way. And then will affect our engagements through the coupling factor, for example. And that's why it's important to calculate the coupling factor. Well, the resonators, we have two resonators for two different frequencies. One is S band at 2 GHz. That is described basically here graphically, where in a resonator, basically you want in the volume of interest, pure magnetic field, and then zero electrical field. This is, I think, never much in reality, but is almost done in this Alderman-Grant resonator. Then we have here a small description, and we see here the radio frequency coil here, we send the magnetic field, and then there is here, right, the coupling coil where you send the microwave. And then the X band, the other resonator that we have, is here in the core described, and there's a cavity resonator here with these modes. And then you see here where is the magnetic field, and then it's perpendicular the electrical field, and then in the region where you of interest is practically zero, the electrical field. Well, as you see, the volumes are very small there. And then now the field cycling at the end is also an experiment to pre-polarize our sample, let's say to enhance sensitivity when we want to study relaxation at low fields here. We first pre-polarize, after that in the fast switching, the magnetization that is out of equilibrium will relax here in this relaxation region. And then after that, we can increase the magnetic field again to the acquisition field here to gain, to gain sensitivity, apply the 90-degree pulse, and then measure the signal. And then this is a typical curve that we get when we have, for example, a solvent and then a radical inside. You get this curve where you see in the black curve describe basically like two steps, and these are related basically with the omega tau, where the tau is the dynamic of the system, and the omega is related with with the electron Larmor frequency or the nuclear Larmor frequency. And the scalar interaction is a pure Lorentzian, described here like this, and then the diffusional part is more stretched Lorentzian. And this is typical what we see in all experiments. Well, let's continue here. It's another scheme where now I want to describe the DNP, basically, experiment. Then in the DNP experiment, we irradiate with microwave. And then what you're doing is you fix the microwave frequency, you fix the frequency, and then you swap the polarization field here in this polarization period. And then you change very schematically here, because this can be more complicated. Then you change the magnetic field from a low value until high value, and then like this, you cover your range in the line, basically. And like this, you can obtain the signal encasement in this way. Where you see here, the central line basically here is due to the Oberhauser effect, and this corresponded to the electron transition, where you see a scalar interaction here in red, and then with a maximum of 1. And then the other one is the dipolar interaction, maximum -0.5. And then here you see basically these two lines that are corresponding to the solid effect, because I show you here, I told you here about this line with function here, this function, and then you see that you have here either plus Fn or here will be minus Fn, where Fn is basically the Larmor frequency of the nuclear. You have this offset. And then how you recognize if you have Oberhauser effect of solid effect, basically with this performing this experiment and see it, the type of encasement. You will see examples here. That means, then describe this, we can see an example of which lines we get when we have, for example, temple in the S-band resonator in water. And then you have 3 lines. That is the one that we are expected, basically. Then we see here the encasement factor. And then these are on the right side here, we have the FIDs, and then you see at this low field, the thermal polarization like this, and then after the irradiation, after the encasement, you get in the field cycle like this. This is one of the first experiments, the field cycling, giving the encasement here of the signal. Actually one of the first in our group observing DNP. And then you see here in comparison thermal polarization, but at higher fields. And you see that you gain huge signal to noise ratio here. Well, now let's try to compare S-band and X-band in different systems. Here we have basically trityl in glycerin, in very viscous system. We have polybutadiene and BDPA, and then crude oil here containing asphaltene, because in the asphaltene is where most people think that are the radicals. And then you see here the encasement curves done by the DNP experiment. And you see here little encasement, somehow, very little. If you can see, okay, here in crude oil, you see something. But if you go to the X band, then what you can see here is a gain in encasement, in sensitive gain. Even though you don't get 100 or 1,000, but you get really a huge, the difference, right? When you work in X band. And here's an example, an application where we have a polymer system, polybutadiene here in benzene, and then we add the BDPA radical here. And let's see what will happen when we perform this DNP, changing here, radiating a fixed frequency in X band, and then changing the polarization field here, we get our, our field cycling signal. Then you see that when you are close to the central frequency, you see here this effect. That means you will see a line that is negatively enhanced, a line that is positively enhanced, and then this is talking about solid effect. And then there is Overhauser effect here. Let's try to see here fast. Going, we'll use this system here. Okay. Somehow froze this. Okay, then good. Then we have the system here, and then it happened that you can simulate actually two curves describing the experimental data here. One is basically the solid effect, and the other is the central line with the dipolar effect going to the negative enhancement here. And then you can see here, if you subtract the two signals, then you can basically say that, okay, you get the enhancement due to the pure Overhauser or pure solid effect. Here on the left, we see basically our signal intensity. And then you see, if you do the other way, then you can get the other signal. I mean, the one that is enhanced by the pure solid or pure Overhauser effect. And like this, we can get the T1 due to the, we get the signal enhanced by either solid effect or by either Overhauser effect, and then we can measure the T1 in the enhanced signal due to this selective way to measure this signal. And then we can associate basically the longer T1 here of the Overhauser to the benzene, and the other to the polymer. And this is basically, let's say, the implications are in our understanding quite big, because it's a way to selectively enhance either one system or other system in a two-component system, for example, multi-component system. And this is quite advantageous and can be done by the field cycling. And then with the field cycling, we can get the relaxation, the relaxivity here of the two species due to this DNP selectivity. And then we can describe this by modeling them. But here we compare with measuring pure, basically, with what Hollywood's dying. And then we have a good agreement with the pure samples, basically. And then we can fit with certain models typical of polymer systems, let's say, in this case, power loss. But this can be, it's not, in this example, it's not important, the model. And then let's talk about the 5-and-dime here, the 5-and-dime, this difference method introduced last year in our group here. And then let's see, if you have several systems here as an example, your polymer, viscous liquids like glycerol or water in silica, for example, porous media, then you can measure a typical T1 experiment, T1 dispersion, T1 in function of the frequency in all the system, right? And then what happens if you put radicals in the system? Then you get enhanced relaxation. Basically, R1 is 1 divided by this T1 that we get here. Then you get the R1 obtained by without radicals, and plus the paramagnetic contribution here. And then you get lower T1 principle, and then you can have different shapes in the curves, and then this shape actually is what is exciting to model, because this speaks about through the models we can say something about the dynamics in the system. And well, we can measure at another concentration here in the respective system. Okay, we add different radicals, and then according to the system, then we see again more enhancement in relaxivity in this parameter here, right? Due to this paramagnetic thing. And then the idea is, okay, the question is, can we get the the relaxation of the, I mean, this value here, the induced paramagnetic relaxivity, yes, if we subtract the value without radical and with radical. But the question is, if you measure only these red and blue curves here, that means if you measure with radicals at 2 different concentrations, can you get the pure nuclear relaxation? And the answer is yes. And let's see here schematically, you have here, yeah, the relaxivity here very schematically, and then you have the pure substance here, and then you measure different concentrations. Then what is known is that the induced relaxation here due to the radicals is proportional to the concentration of the radical here through this equation, at least in the low concentration limits. And then this R1 is the curve that we know already. And then if you determine then these 2 curves here, and then you combine these 2 equations, you can get, yeah, it's very, very simple, you can get the pure relaxation without the influence of the paramagneticity or the electron or the radical. And then this is of interest if we cannot access basically the pure relaxation of the nuclear. If we talk about low sensitivity, low concentration of nuclear with low gamma or low natural abundance, then this method could allow, or is allowed, we prove it, to measure the pure relaxation, nuclear relaxation in presence of radicals. And then this is called 5-andime with this complex name. For the people that knows our group, you could imagine from whom is coming this name. Well, also you can get as an addition, of course, the radical induced relaxation here. And let's go now to describe systems in the last part. I mean, concrete examples. Here we have SVS solution, and we measure here in a copolymer. This is the name of the copolymer. Here we have polystyrene combined with polybutadiene in this block copolymer here. Actually, 30% of the polystyrene. That means you have 15% in each of these extremes here, and then you measure here. I mean, we measure. I mean, we combine this with tempo radical, and then you perform this DNP with 5-field cycling. That means you irradiate at fixed frequency. You change the polarization field. You swap the field in the EPR offset frequency here. Yeah, this is basically the magnetic field. And then you obtain these enhanced curves here, basically the DNP spectra here. And we can see that in the radical, you can distinguish the signal of the PV and the PS. How we measure with CPMG in the acquisition field, and then you can fit 2 components in this decay of the CPMG path sequence, and then you can ascribe or set these 2 components to the part of the copolymer, and then this is if you compare intensities, you see that this is right, and then you see here, and then seeing the enhanced of one component or the other component, you get this spectra here, and then you can even get here the I mean, changing the power. You can change here. You can say here the enhancement. And this is telling us, if you recognize, I mean, because tempo has 3 lines, it's telling us that you see here Oberhauser effect because the spectra is on one side, let's say, curve, simply speaking. And then the most enhancements, you see it in the PV here. And then the PS is not so much enhanced by Oberhauser effect. But now, if you see I mean, if you change radical with BDPA, then you see here that contrary now the PV is not so enhanced and the PS is enhanced, but you see here this typical signature of the solid effect in this curve. That means in the PV, basically you have Hauser enhancement, and here in the PS you have more, let's say, solid effect. But okay, this is roughly speaking. We have to see in detail this curve. Here we see a small asymmetry. Here in this curve, we can say that there is a combination of these two effects. Then you see here there's the scalar here enhancement due to the positive enhancement here. And then this is a nice result because changing the radical and using T2, let's say, resolve fast field cycling, you can basically say something about the enhancement of the two different components. Then again, you are selective in one of the two components, right, of this polymer system. Well, continuing with this polymer system, let's see what happens if we can measure a different concentration and if we will be able to recover the pure nuclear relaxivity. And here we see two different fast field cycling experiments at two different concentrations, not with DNP here. And then you see the different curves here, a different relaxation, and then discriminating into the components of our polymer, you see that the components here. And then basically, if you combine these two signals at different concentration and doing this 5-and-dime method, you get basically what we call the recovery curve of the pure PS or the pure PV, and then we can just measure the thermal polarization of this PV and PS when it's pure, and then we see excellent agreement. I mean, we see that the 5-and-dime method is here really working. Let's see how it's working now. Sorry, and then here we apply models to describe this relaxation of this copolymer system here. I mean, at the end, we want to study dynamics, and then we have to describe fit spectral densities that will describe the dynamics here. And then another type of system is a native native oil-based radicals that are in native oil. For example, we have an oil that has asphaltene here, and then here we can describe. I mean, we can do the experiment of here T2, T1, and then here we can distinguish three components, and these three components can be basically associated to the basically the asphaltene or resins times, or the part, sorry, of this complex system that is oil, or can be basically the saturated part, also that are more mobile, right? And can be also the rest of the part that can be aromatics. And then these are the three parts that we see here. I mean, that we can distinguish. Basically, of course, that we have analysis of the oil with this famous, I don't know, but this known analysis that is called SARA, yeah, what is giving basically the aromatic, the saturated, and the asphaltene portions of the oil. And then like this, we can say that, okay, asphaltene and resins give a signal, the saturated and the aromatic give different signal. And then discriminating in these three signals during the CPNG, then we get these curves here. Then if you do this DNP experiments, you see here that you see solid effects basically associated to the asphaltenes, basically here. And then you see here the curves in function of the power. Basically, oh, sorry. went too far. Basically, the saturated aromatic and asphaltic resin components are given the different enhancements, and then the maximum enhancement will be given basically by the part that contain the asphaltic and the resins, and the lowest will be basically the more mobile system that are the saturated part of the oil here. And then another oil that contains vanadiol, and then here we can distinguish two components when we perform relaxation experiments here. And then if you do field cycling, we can see the different components here have different dispersions. And then you can do also here DNP fast field cycling, compare this with the APR signal, but then you will see here the signature of the solid effect in this system, and you see here enhancements, not so great enhancement, but enough to see the presence of the solid effect here. Well, this is another system where we have lithium chloride solution. Then we want to measure in lithium. I mean, this is lithium NMR in field cycling. And then the idea here is the same, applying, try to measure at different concentrations, and then try to get the pure relaxation, the pure nuclear, let's say, relaxivity by doing 5 and dime. And in this system, it's nice because you have the little lithium molecule water and then the big tempo, and then here you can apply. First of all, okay, you can do DNP, and then you see here the different enhancements at different concentrations. Then you see that when you have a much bigger concentration here, around 90 millimolar, you have to consider here Heisenberg exchange. But then you have here the enhancements. And then basically here we can try to work out to find here the maximum enhancement here, and then at the end to find the coupling factor. And then we see that the coupling factor can be found here, and we can check the model. You see here we have considered a Heisenberg exchange. Then at the end we can see the curve that if you consider that the lithium didn't have any relaxation, any dispersion, at the end you can model this basically the relaxation through the models that describe the induced relaxation by the radicals, and this is a fitting performed considering here on the lower part considering diffusion, and here on the upper part not considering diffusion. And we see here different correlation times not so far to each other, but refining the model, if we believe in this, we get here the corresponding diffusion dynamics. Well, this is another system where we have deuterated benzene in silicon particles, and then you see here typical dispersion of liquids in porous media, and when we measure here the deuterium, we can see here that we can perform actually 5 and dime. We measure at different concentrations, and then we can get this recovery curve here. That on the other way, if you measure, you see that the red curve is the same as the red curve here, and then here is measured without a radical, let's say, the field cycling experiments, and then you see much more dispersion in the data. I mean, in this case, performing 5 and dime, you have a much better sensitivity in doing this dispersion experiment. Well, here, with the last slide practically that I'm going to show is related with the measurements of a system with low natural abundance, carbon-13, low nuclear, low gamma. Yeah, this is carbon-13 in benzene, in deuterated benzene. And then here, you see that we can measure with the DNP. You see with different radicals, you see the signal and I'm sorry, not the signal, the dispersions, and even you can compare these. I'm sorry, this is an experiment done in enriched carbon-13 benzene deuterated. And then you can see here that you can measure it, measure the dispersions, and then you can obtain the recovery curve here. And in this experiment, we show that you can measure actually carbon-13 nuclei in this sample, but in natural abundance, not enriched. And this is, you see here, the enhancement that you get here that makes possible these measurements of this low abundance and low gamma nuclei. And then, as an outlook, we can say that well, DNP helps in the determination of the molecular dynamics of these systems of system of interest combined with radicals. Basically, you can perform selective detection schemes, either selecting the Oberhauser or the solid effect, or simply basically also performing selection by the relaxation, the relaxation, for example. And then the difference approach, the 5 and 9, was applied in several systems, and it's working quite good. And then also in crude oils, we show that the native vanillin complexes actually are acting as a polarizing agent for protons in these oils. And last, we see basically in X nuclei potential of the use of 5 and 9 and then possibility of see this X nuclei in feed cycling. And with this, I finish, and thank you very much.